Morning. Thanks for all for coming. If you don't know me, my name is Jacob Torrey, Mr. Jacob Torrey. I know sometimes you get the automatic PhD for being here, but Mr. Jacob Torrey is just fine. I'm very excited today to be here presenting a project that I'm quite passionate about, intent-to-find adaptive software. I think that this is something that is a real need across the DoD as well as the government and kind of the industry as a whole. And so hopefully I can convey some of my excitement, get you guys jazzed up about this as much as I am, and hopefully answer kind of any questions. We will be taking questions. There'll be some pieces of paper distributed. If you have questions throughout, then they can be passed out to Eric, Daryl, or Mark, who are currently sitting in the back, and then we'll be able to review those and answer those after Mark's briefing about the BA process. So in a nutshell, what IDAS is trying to do is trying to look at how we develop technologies, tools, workflows that allow us to capture the engineering intentions and decisions, thereby allowing us to develop software that enables rapid adaptation of software-enabled systems. We'd like to try to bring more automation to bear in the software sustainment loop so that DoD systems that last a very long time can remain relevant to today's problems and tomorrow's problems without expensive and tedious modernization cycles. Today, the federal government spends about 70% of their IT budget on O&M, maintenance, software sustainment, and maintenance. That value has been going up over the time, and we're slipping further and further behind. The number of systems that are still running Windows XP and the estimates for when they'll get to Windows 10 is still after Windows 10 will be far end of life. So we're not catching up with our modernization cycles. Instead, we're falling further and further behind. Software is very brittle today in terms of changes of requirements. When you're looking at the life cycle of DoD software, which could last 50, 60 years, some of the assumptions that were made during the software engineering process are probably going to be wrong in the next 50 to 60 years. Software today and the ecosystem is very different from what it was back then. And we don't have the luxury of being like some of the commercial sectors who say, oh, your phone is 2 years out of date. It's no longer supported, throw it away and buy a new one. We can't really afford to throw away an aircraft carrier after every 2 years and try to buy a new one. Me as a taxpayer would prefer we don't do that as well. Why do we think this happens? I think a lot of this comes from the fact that software can be very, very complicated. In the physical world, when you're engineering a physical problem, there are laws of physics that we can't really control that help to constrain the problem space. CAD tools won't let you build walls that are unsuspended, floating in free space, so they can naturally limit the complexity. You can write software that's as MC-esterish as you'd like, and I've seen some of those software packages, like the staircase that is always going up or the self-fulfilling waterfall. A lot of that, what happens is how you manage that complexity. We're going to come up with a term that we're calling concretization, or making something concrete, from abstract to concrete, which is when a software engineer, during the process of solving a problem and writing source code to solve that problem, basically looks through and says, all right, there are many ways I could solve this particular function. I could write this, I could pick this particular value. There are a lot of them that are apparently equivalent or mostly equivalent. I'm going to use my many years of experience, my training, any conventions or guidance that I have in terms of what my company standards are, or other types of experience to be able to pick the best value for whatever best might mean. And that's what we do as engineers. We apply heuristics and we try to optimize over a very large set of competing values and make the best fit. Unfortunately, when something like that is going to be then hit with very high amounts of change, the best fit sometimes changes pretty often. So some examples that have come and are specific issues that we've concretized in the past and then had issues with is assuming a network latency will never exceed a particular value, and you're building in some conservative estimate for that. Perhaps you're selecting a particular type to store information that may not necessarily be the right value. In particular, selecting a 16-bit integer to represent the horizontal velocity of a rocket. It may seem fairly far-fetched, but this was actually about a $364 million bug in which the Ariane 5 rocket reused software that had a 16-bit value to store the horizontal speed, but had a very different trajectory. It essentially overflowed, caused an error bit to set, fired all of its horizontal thrusters while it was still in orbit, and blew up. Something as minor as picking a bit type You have the context in your mind of what the orbital trajectory might be and all of the constraints there, and you reuse that software in a slightly different context, and you're no longer correct, to sometimes pretty disastrous consequences. We're also seeing this today, even as we move to the cloud, which provides us elasticity and agile options to be able to move even between vendors. We're still getting stuck on APIs that need to change. Otherwise, we're getting locked in whether or not we like it, because we are fixing to these static APIs through concretizing to a particular type. So software concretization makes this software brittle. I talked about this, is that typically when you're making these decisions, you're either designing your software or you're writing your software. If that software has to go out and persist for many years, it's likely that those will be wrong down the road, and that can be a bug or a very difficult thing for you to go and retrofit out and figure out why you made all of those changes and how to go back and safely do it and adapt it to a new context. You also sometimes end up with inefficiencies where you have to choose the worst case scenario or the expected most conservative value to be able to make your software work for that one case. So imagine an e-commerce site might need to provision servers and set up a database regime such that they're going to be able to handle the load on Black Thursday or Cyber Monday or whatever the day is that gets the most traffic, and then they have this spare and kind of inefficiency running the rest of the year. Now the cloud has allowed us to scale that a little bit, but this type of thing shows up in other types of systems as well. And as I said, a lot of these decisions will be wrong in a different case, or a different point in the future, or if we're trying to reuse software, a different context, when we're taking that software and we're plugging it in and trying to use it to do something that's not quite the same, but close enough, and hopefully it'll save us a lot of money, that's when issues happen. And I think as software people, we're a little bit treated unfairly, because we would never ask an engineer to go and take the same plans that they built for the Golden Gate Bridge and put it across the Potomac without re-engineering or looking at the soil samples and maybe looking at whether or not there's going to be flooding or not. But it seems like sometimes software projects have the same type of thing. Well, it worked in that rocket, it'll work in this rocket. And so I think a lot of times we're also asked a little bit more than maybe some people in physical worlds, because it is a little bit ridiculous to ask someone to reuse plans without ever adapting them in the physical world. So that leads us to the goal of this program. How do we capture that entire space of viable options to allow us to move within that viable space in a safe way down the road to improve the automation that we can bring to bear in terms of adapting that to future needs? So can we defer those concretizations to allow us to adapt to future changes in resources, platforms, and requirements? And that's what this program is really trying to figure out. Can we do that? How do we do that? And let's demonstrate that we can do that. A very, very simple example on the top. You have some requirements which may be provided to you in a very many-page Word document. It may be something that you're slowly figuring out in a more agile way, where you're trying to kind of figure out what the minimum viable project or the MVP of a solution is. And then you have conventions, intuitions, other types of things that you're trying to use. Typically, these are either passed around informally, implicitly, or in human-readable format. And then the little developer guy right there will follow those conventions and use their intuition, their experience to try to implement these requirements into code, which is now the software artifact that you need to carry around with you, and then that gets compiled. If something is wrong in this software artifact, it requires a pretty extensive human-in-the-loop adaptation. If you change one of those requirements, you have to go through the fairly expensive manual process, not only of just re-implementing, but also figuring out possible kind of pieces within the code that have tangentially been impacted, like the choice of a particular type of variable, that now you need to go back and re-examine the context in which someone made that decision that probably doesn't even work at the company anymore. That's very much human-in-the-loop adaptation. What IDAS is hoping to be able to do is to be able to go towards more of the human-on-the-loop adaptation. Can we take these same types of things, requirements, conventions, human intuition, knowledge, can we formalize them in some way, hopefully in a fairly low-friction way that traditional developers would be able to do and be able to adopt, such that we have some kind of IDE environment, workflow, learning mechanism, annotation framework, what have you, that generates some type of kind of hard or soft constraints and intentions of what you're trying to do and what the kind of bounds on that space are that make a viable section that you would have picked a particular point from before. And then again, this IDAS workflow will try to generate source code or work with humans to reduce the lift to be able to generate software. That way, if any of the requirements change, you're just changing something that's much more semantically accessible to that automation. Kind of as a vision is that this is a particular instance where you want to be able to query data on a particular cloud vendor. Each cloud vendor has different types of storage options with different APIs that are optimized for different types of things. So if you wanted to do very high volume, slow lookup, you might use one product. If you want to do very fast lookup or you want to do regular, there might be a different one. If you're trying to represent this problem, might be what's in your head, is you want to be able to search data, in this case, very quickly. So they'll use a particular cloud file system that's maybe optimized for reads or lookups to be able to search that. The things highlighted in red, that might be uncertain. Those assumptions that you're going to be constantly tied to one vendor for the lifetime of that software may not necessarily hold for the lifetime of that software. So how do we identify that these things may be subject to change without necessarily building out an abstraction layer? And then be able to represent the problem in a more abstract way that's not tied to the specific implementation for a particular vendor. Then we have some partial code generation, and then we have to understand what uncertain do we have left. What are these spaces that we want to collapse and make a piece of software that will run in a particular instance? And how do we pull out and find what the context fits for today? So now we want to move to Cloud Platform B. Some type of routine will kind of help that source code be concretized as later process and hopefully an automated fashion that allow us to create a specific software instance of that. So hopefully you get an idea of what we're trying to do. Now hopefully this will help us figure out how we're going to try to get there. So the IDAS program is split up into 4 different technical areas, or TAs. Technical area 1 is automated software generation, intent capture. Basically, how do we create the next paradigm for software development? I really would love for this to be in 5-10 years when you're all here and I'm long gone, and you're going to get awarded for another program, and you go and you open up your computer to start writing your first line of code after the contract's been signed. You're going to go in and start writing it using some IDAS tools and technologies. You're not going to go and open up NetBeans or Java or whatever you're doing today. I hope that we can create something that's so usable that we'll actually want to use it, and we will use it without being forced to by contracts. TA2 is looking at problem set generation. How do we inject realism? How do we expose on a very relatively short time frame software to the types of changes that have bit us in the past? How do we make sure that what we're doing is we're dealing with the right types of changes? So that's looking at how do we understand what types of requirements changes are realistic and have far-reaching technical challenges to be able to address. TA3, integrated test and evaluation, is understanding the different approaches in TA1 and making sure that we're tailoring our examples to things that are minimizing the unnecessary engineering lift while maximizing the differentiation, the results of our experiments. And then finally, TA4, experimental control and transition. During the majority of the program, they'll be serving as a control team. So they're an agile DevOps shop that's not going to be using any additional tooling or techniques that's developed as part of this program. And they're going to be doing the same challenges as us. They're going to be exposed to the same types of requirements, churns, new platforms, new whatever, and see how well agile methodologies work. We're at a turning point right now within the DoD where some forward-leaning organizations are adopting agile and DevOps, and they're very much saying, look at the software written 20 years ago with the waterfall method. This software is terrible. But I haven't seen a clear argument that the software that they write in agile methodology today in 20 years will be a shining example of perfect software engineering and clarity. And so at this point, before we fully commit to that, I want to understand what does it look like for software to age 5-10 years if we can simulate that during this by a traditional software development company using today's industry best practices. A little bit more detail on TA1. This is this engineering framework to be able to capture intent, figure out how to track that, because we're losing something when we compile code, and we do this kind of very one-way function of going from what the problem is down to the source code. What do we need to keep to allow us to be able to back that out and very quickly adapt that? And there are some challenges. We've tried doing this. We've tried saying, hey Siri, write me the F-35 flight control software. Program synthesis is not a new dream. It's been out there for very many years. And there's been some challenges. I think one is the simple single-step synthesis by going from hey Siri or trying to represent that as a very high-level constraint. Typically, it falls back onto some kind of SMT or MILP solver, which is exponential and doesn't scale to the DoD needs. If you represent the problem and the solution in the same way, if you're forcing your developers or your business people to understand software to be able to encode their problem in a particular implementation, which is the human nature and what we do today by kind of concretizing, it's very difficult to separate them and really get that type of adaptation, that modularity. And in the real world, or at least the DoD world, there are errors and edge cases. You can't be in a perfect theoretical CS environment where there's never going to be an error or anything outside of the scope of your perfectly defined Turing machine simulation. We need to build software for the real world. So I have a couple possible approaches. Do not treat these as 3 swim lanes or 3 buckets. These are just a few kind of experimental things that I've been looking at, but we're planning on multiple awards. I'm looking for diversity in TA1. So I'd like to see as many approaches as seem like they might be able to really reach that goal of reducing human-in-the-loop sustainment time and something that could be transitioned. But to go through it, model-based software engineering, forcing developers to think at higher levels of abstraction and deferring some of the decisions about ports and APIs and whatnot until a later step of the process. I've been looking with some very powerful, or working with some very powerful type languages. IDAS, for example, is one that has a dependent type theory. I was actually able to write a function definition where its type signature encoded not only the functional characteristics, but also the performance characteristics. I was able to say, I want this to asymptotically run in an efficient manner. I could farm that off to anyone, be it a machine solver or a very junior developer, and trust that it wouldn't compile unless they had done a relatively efficient sort or searching algorithm. I've never been able to do that in something like C other than by deferring to convention or trusting human intuition. So there may be something there as well. That being said, it's a fairly onerous process and I'm not the best at it still. So how do we make this approachable to a junior developer like me? And then finally, there may be some learning-based approaches. I think on Muse, we were able to explore source code as some type of interesting data to be able to see what you might be able to learn from it. Can you see if there are patches being pushed to a lot of GitHub repositories as they move from one API to another, and there may be some gotchas there that you didn't necessarily do? Can you learn from that process? Can you learn from the CI/CD pipeline to be able to figure out and help annotation and capturing that intent in a way that might reduce that developer friction? So kind of in a high level, how do we have the human in as easy a way as possible? We want to work with existing developers, not replace them with, the CEO. That was the promise of SQL, is that you wouldn't need programmers anymore. The CEO would sit at his computer and write SQL statements. I don't think that's feasible, at least not yet, until Siri gets a lot better. But I think that we need to figure out how do we work with traditional developers and make this something that they're going to want to pick up, and then there's going to be business case to do that. So how do we define this intent in some more abstract representation? How do we understand where our uncertainty is? How do we hedge against that? How do we verify against these constraints that make sure that when we do this adaptation, we're doing so in a safe way? And then also, how do we make sure that we're writing software that's kind of coherent, optimal, and works to the performance needs and the non-functional requirements of the new domain? Strong TA proposals should look to address the following. So how do we capture this intent at design and development or even adaptation time? If you're doing some adaptation time work, how do you start reducing the load and the legwork by bringing automation to bear there? How do we separate that intent from the in particular concrete decisions of a particular instance so that we can work at that level of abstraction without having to kind of go in and back that out from very particular and sometimes messy spaghetti code? How do we write this in such a way that, how do we make an argument that these methods could be learned and adapted by traditional developers without a very deep logic or formal methods training? So during phase 3 of the program at the end, if we've been able to demonstrate that the TA1 methods are better at adapting to changes and requirements and are maybe lower cost or more supported and more maintainable, the plan is to give those tools to the TA4 control team and then run additional exercises to measure their learning curve. So that you imagine you need to think about what a traditional developer running at a particular agile dev shop would like to use and what types of methodologies you might be able to use to make that something approachable for them. So this can really get brought in and kind of mainstream adopted. What types of automation can you use to be able to generate or adapt software to these new requirements? How do you reduce human in the loop in that longer sustainment tail? We're going to be able to try to hopefully play out requirements changes that have happened to us in the past and play that forward off of some of these exercises. How do we understand and how do we quantify that human-in-the-loop reduction to make a compelling argument that people want to use these tools and that they should use these tools? And then finally, what kind of evidence or assurance can we provide that when we've done this adaptation process, we feel reasonably confident that we're safe in using this software and we don't necessarily need to go through the same exhaustive testing. During this program, we're going to not be looking at safety critical systems, so we don't have to worry about necessarily the same bar, but showing that this approach could work with future engineering and other domains is a strong suit. Going into TA2, so this is about how do we understand what the problems that have been facing us over the last, say, 5, 10, 20 years have been there, and how do we develop these in a way that don't have any security sensitivities of a particular DoD relevant issue, but draw from that to be able to make sure that we're kind of testing at something that's realistic for how this tool should it transition. So they're going to be acting as the customer during our 1 to 4 month exercises. And they're going to be essentially developing a series of requirements changes where you start off, you have some period of time to warm up and build a system that does X, Y, and Z. And then once everyone has delivered that and it's satisfactory, then, oh, sorry, the requirements have changed. You have 1 week to rechange. Or, oh, our VP of sales went golfing with this particular vendor, and now we want to switch from your NoSQL implementation that you picked to a particular much more expensive one, but we already bought some licenses for that, and he'll be by next week to see how it's coming. So this type of fairly realistic policy changes or other types of real-world changes that come at us from left field that are very difficult for us to anticipate and build abstraction layers ahead of time, build those out, and then act as the customer. So we're going to look at 3 different problem domains. To prevent this simply being a very domain-specific exploration, we have 3 problem domains we're going to look at during the course of this program in these different exercises. 2 of them I will tell you about today. The third, TA2, will bid as a candidate and will be announced at the kickoff to prevent anyone from pre-concretizing on who they are either staffing up or their approach to make sure that this is a fairly generic and general approach. So the 3 are logistics, the held back one, and cloud agility. As an example for logistics, right, you're tracking very different types of inventory across a different, very large place, the world, and you have different means of getting them there. The inventory is very much non-fungible, and generating a generic schema that should track everything where food may expire and plastic goods might not. Some have particular handling constraints, like lithium-ion batteries are not supposed to fly. And some of these requirements have kind of come up after there's been a fire or disaster. There was no way for you at design time to say, lithium batteries will start catching on fire in the next 10 years, so I'm going to have a special case in my database schema for them. Also, import-export laws are very different between locations, and they can change on a fairly frequent basis, impacting costs. Tariffs can change quite rapidly, and a lot of these things are happening outside of the control of the software. How do we handle this new legal requirements that have happened and be able to handle these very strange and different types of devices? And so that's an example of a problem domain that you'll see these requirements change over the course of an exercise. And TA2 will be working to inject realism based on past challenges within the logistics domain. Another one is cloud agility. So I think infrastructure as a service and maybe even platform as a service has been fairly well commoditized. Tools like Kubernetes allow you to build up your instances in your Docker containers, and you can pretty easily shunt them from one cloud provider to another, to on-prem, to partial. But to move up the value chain, they're offering more complicated software as a service offerings. Things like machine learning services, going out to humans for like mechanical Turk type offerings, these types of things that are very vendor specific and may not necessarily have one common abstraction framework. That induces lock-in. So how do we move between these higher level value chain services that are not just, here's a Docker execution framework? We also have had very recently in the news legal changes that have changed the abstraction fundamentally of the cloud. The cloud was originally sold as this locationless everywhere service that you could turn on anywhere. And after GDPR and after California has ratified different legal requirements for tracking policy, a function that spins up in some slack space of an instance on a server needs to figure out where it's physically located to make sure it can legally comply with the borders of where it is. So if you write a function, it may need to behave differently and know information about its inputs in a different way if it's in the borders of Europe versus the borders of Virginia. And that came out, and that very much broke the abstractions. Typically, serverless applications don't know or really care about where they are operating. And now you've now legally required them to change their behavior. And this can come with pretty severe costs. In the news 2 days ago, I think a particular company was just hit with a almost $200 million fine for violating this. So this is a very severe thing that's been very difficult because there's no abstraction layer for the balkanization of the internet and the legal frameworks when you're trying to knit this all together. So strong proposals in TA2. How do you generate exercises that are able to expose all different parts of the software development lifecycle to changes that are realistic across requirements, platforms, and the resources available? How do you protect and abstract any security sensitivities while bringing the realism but not necessarily any of the sensitivity? It is our hope that after we go through the necessary reviews and after the exercises, we could release these problem sets to the open, broader community so they may be able to use these as well. How do you show that there may be challenges with scalability without making everyone write a 10 million line piece of code? Formal methods has been able to get to larger and larger code bases, but at some point the scalability at maybe say 1 to 10 million lines of code starts falling apart. How do you test that scalability to make sure we're not all writing generations that work on the hundreds to 200s or thousands of lines of code without making everyone go out and spend a lot of DARPA's time and resources writing 1 million lines of code for no reason? So how do you figure out how you can remove the engineering effort while still getting good quality scientific data? TA2 will have to propose a third relevant domain, explain why it's significant to the DoD or the nation, and understand what types of events or changes will trigger adaptation or require requirements churn. Things that are very difficult to predict are encouraged. And then finally, since TA2 will be the end customer for these exercises, you're going to have to represent that customer in a way that makes sense for the various TA1 and TA4 performers. So some may request the more traditional DoD, here's a 300-page Word document, slimmed down a little bit, and we're going to go off of that, where others, using more agile methodologies, may want to just sit down and talk with you and understand your business case to do that kind of minimal viable product, results or requirements analysis kind of with you. So you need to understand the domains and the problems and requirements well enough to be able to do these. And then finally, we have TA3 and 4, experimentation. So TA3 will be validating the results coming in from each of these exercises, working to tune and guide TA2 to make sure that we're challenging and differentiating our performers. How do we make sure that we don't run in a 4-month experiment where everyone fails or everyone succeeds and it was very easy? We're not really able to understand why and the differences between both TA1 and 4, but also between the different TA1s without being able to do that. And then they will also manage that separation. So they'll be the go-between between TA1 and 2, between 1 and 2 and 4 and 2 to be able to understand and figure out, okay, how do we tweak these so that we make sure that we're able to kind of, based on TA3's understanding of the different approaches in TA1 and TA4, build these challenge sets to get the best value of our limited experiments. TA4 is the transitioning and experimentation control. So this should be a competitive software vendor with an agile or DevOps-based approach, basically industry best practices. And they'll be, during phases 1 and 2, essentially competing as an experimental control, doing the same set of requirements changes following industry best practices, and we'll see how well they age over a kind of compressed time cycle of changes. In phase 3, as I mentioned, we'll provide the best TA1 technologies to them and measure their learning curve. The hope is at the end of this program, TA4 will have been beaten soundly by a particular approaches or set of approaches. They'll have drank the Kool-Aid and they'll want this tool, and they'll be spun up and jazzed up and they'll know how to use it because it's something that they can adopt, and then they'll be using that and bringing that to bear on all their future efforts. This is a way that we can start to create a very grassroots kind of commercial incentive to do this transition, because there'll be established players in the industry that will be using these tools and demonstrating that they are in fact better than they even themselves were. So comparing TA1 versus the TA4 control, looking at the human effort. So during these exercises, we'll be tracking FTE effort per exercise. And so we expect in phase 1, there'll be more effort than just writing the code from scratch. It may take a little while for the tooling and the technologies to catch up. but we'd like to see that kind of scale down to being an order of magnitude less than traditional development time at the end of phase 3. The human skill set also, in the beginning, we expect this will require someone who's very well versed in your particular approach. Maybe the PI will be participating very heavily during these exercises. We'd like to see that trending towards something that a traditional developer could do in the end of phase 3, because that's going to really feed a transition and adoption. If the TA4 performer doesn't have any interest or any knowledge or any background, they need to spend a year learning formal logic to be able to use your tool, it's probably not going to trend very well in that course. And then also, how long does it take to go from formalizing and representing the problem to being able to actually have a specific instance? In this case, we're expecting this to go down and hopefully on the order of about an hour towards the end. And that fits in very well with the kind of informal slogan of an agile sprint in a day, where you show up to work, you kind of formalize your requirements, you understand what the customer is looking for, you represent your intent, you go to lunch while it's generating a particular instance for you to test, and you spend the afternoon testing, and now you can respond to customer queries and interactions in a day rather than on a 2 or 4 week sprint. Strong TA3 proposals. How are you going to guide the TA2 problems to make sure that we're getting the best value out of our limited experimental exercises to be able to differentiate and maximize the value to the government for the program? How do you make sure that TA1 is complying and TA4 is complying with these problem sets? These requirements may be ambiguous or very difficult to empirically measure. How do you do a fair comparison when some of these requirements may have ambiguous natures to them? And then how do you measure the performance both of TA1 versus TA4, as well as understanding the differences of strengths and weaknesses in between the multiple TA1 performers? And then strong TA4 proposals, showing a track record of applying industry best practices, so agile or DevOps paradigms, and producing large or complicated software systems, preferably across a broad spectrum, not simply just applying the same kind of web app software as a service cloud provider, but being able to use these tools in other domains would be a differentiator. It'd also be great to see past use cases where agile development was used to be able to rapidly adapt to these types of changes, or where a very minor requirement change that everyone thought was going to be done in half a day ended up being far more painful because of that kind of cascading effect of some of these decisions that have been stuck. So the exercises will be worked at your performer sites, so you don't have to all travel for 1 to 4 months. But the exercise will be something like this. There'll be some problem domains of DoD relevance. These will be cloud agility, the logistics, and the held back domain. TA2 will kind of research this during the duration of the program, understand where the realism, what types of requirements are very difficult for software to adapt to, but of ones that actually show up relatively frequently, and build out basically a time series of requirements with a notional pacing for how those will be released. TA3 will work to guide to make sure that we can differentiate those and make sure that we're getting the best bang for our buck during these limited engagements, and then pass those out at the same time to all of the TA1 performers and the TA4 control, who will then generate candidate software to go back to TA3 for evaluation, and then getting the next bad news envelope of the next requirement change. At a high level, it's a 4-year program. The total funding available for award is about $65 million. As I said, we're planning for multiple awards, and we're looking for a diversity in TA1 approaches with a single award for TAs 2 through 4. High level, there's 3 phases. Phase 1, 18 months, is looking at how do we kind of build up and scaffold this. So there's going to be a couple exercises that are essentially testing, just for us to work through the mechanics of how these work, so that we're not munging that with the actual differentiating and performance of the capabilities. So the first test exercise will be optional for TA4, and then that will conclude with another test exercise just to get people in that mindset and figure out how this works in terms of how people want their requirements, what the pacing will be, to start to get that figured out. Phase 2 is kind of this core cycle of doing these evaluation exercises, and we'll be cycling through these different problem domains to show and force people to look at how do we do this in a very general sense. And so we'll be doing a bunch of evaluation exercises. And the hope is that phase 2 at the end will have demonstrated superiority over TA4, and then we'll take the best, most promising capabilities from TA1, provide them to our TA4 performer, continue doing exercises and continue maturing those capabilities to measure what the learning curve might be. And hopefully TA4 will be just as productive at the end as the TA2 or the TA1 providers that actually built that software. Proposals can address only one technical area, but you can submit proposals to multiple technical areas. That said, which one is considered is at the discretion of the government. And then finally, the only two TAs that can be awarded to the same organization is TA 2 and 3 to prevent either appearance of or an actual conflict of interest. With that, I believe I am done. I will caveat all of this, say that the BA is not out quite yet, and so I encourage you to refer to the final word, which is the BAA, when that is published, hopefully in the next day or so.